weeks we actually talked a little bit about principles of motor control. We talked about descending pathways, and we mostly concentrated on the, after describing descending pathway from the brainstem, we concentrated on the pathway from the corticospinal, the pyramidal tract. So basically, we actually, at the level of the brainstem, we describe two motor systems. The first one is a voluntary motor system, and the second one is a postural. Most of the brainstem pathways, or the medial pathways, and we described about 3 different pathways, are actually postural system, postural control, right? All the vestibulospinal, the reticulospinal, and the tectospinal are pathways that are involved with controlling posture and balance. And the cervical termination, the spinal termination at the cervical level is on the medial sides of motor neurons. We then described a little bit about the rubrospinal tract that is part of the voluntary control, and that terminates at the spinal level at lateral portion of the gray matter where motor neuron pools of distal muscles are located. And then we said that, we described the corticospinal pathway that first has access to these two systems and is mostly involved in the control of involuntary movement. Okay, so now today what I would like to describe is a little bit about the motor cortex, because in fact what we think coordinates the entire activity of control of voluntary movement is the motor cortex, and I'll talk about the motor cortical maps, coding schemes that are considered to be existing in the motor cortex. I will show some set of experiments that talked about coordinate transformation in the corticospinal system, and then I'll talk a little bit about sources of input to the motor cortex. Okay, so first of all, when I talk about motor cortex, I mostly talk about the areas that are rostral to the central sulcus. We're talking about the primary motor cortex, area 4, premotor cortex, and premotor areas that are area 6, supplementary motor area, and some additional motor areas that are located deep in between hemispheres, the cingulate motor areas, that are related also to limbic, to actually coordinating between the limbic system and the motor control. There's a large influence of the limbic system on our motor activity, which is mostly mediated by the cingulate input. In addition, non-motor areas are also important for motor control, and these are the primarily the somatosensory cortex that we know have a lot of interactions with motor areas, and the posterior parietal cortex, area 5 and area 7, that are coordinating, they are part of the reach and grasp system that we will try to talk a little bit maybe later. Okay, so people are really trying to look for maps, and because maps makes kind of makes sense in terms of organization. And we know that in sensory areas, people are talking of multiple maps, sort of a representation of the world onto the relevant cortex. And also in the motor cortex, people were looking for maps for many years. I think the first experiments were done at the beginning of last century by Layton and Sherrington, that they actually studied stimulated areas in chimpanzee and orangutan and gorilla, and that at the time people didn't understand anything about the functional organization of the cortex of the area, so they stimulated everywhere, and they found that there is a site in the cortex that produces that stimulation over this site actually produce a discrete contralateral movement. So, and they mapped and they found that there is some sort of a rough representation of the entire body on this area. This is shoulder, elbow, and wrist, and they kind of suggested that this is the motor cortex is. So first they called it the motor cortex, but also they suggested that this is sort of a synthetic organ for motor action, because based on these maps, I mean, you can say, well, if I want now to make movement that involves the shoulder, the elbow, and the fingers, all I need to do is to excite in an organized manner these areas, and I'll get this movement. Now later on, Penfield, who is really kind of started the entire concept of motor map, the motor homunculus, but also like mapped the entire again different brain areas. He was basically a neurosurgeon that during surgeries he stimulated different area of the brain and tried to understand organization and issues like mental processes that he was looking for, and he actually showed, and all this work was done in humans that went through some brain surgery. So you expose the dura and you stimulate over the brain, and what he described is a sort of organized homunculus that had all the properties of homunculus that people found in sensory areas. The entire body is mapped, but not necessarily in a proportional manner. There are areas of our body that are highly represented. Okay, so the cortical area of the motor cortex that is devoted for different sites is not necessarily proportional to the size of this, of the number of muscles that innervate this part. And later on, Woolsey found similar homunculus also over the brain of primates. Then you can see that the leg is at the medial part and more lateral. You see the hand, the arm, the hand, face, tongue, etc. Okay, so kind of in a sense, I mean, this is sort of a more detailed description of exactly which site you can find, and these are different. Again, this is people have done a very, very detailed study of exact representation, kind of assuming that if we understand the representation, we'll understand the action of the motor cortex. However, already here you can see that the system is not, the representation is not continuous. So for example, this is the 4 chord digits. They have multiple patches within the motor cortex that stimulating in these patches will produce finger movements. So the map is discontinuous in the manner. And this is sort of was later on shown in a set of really heroic experiments that were done in the 70s, where people will, today we're all trying to collect as much data, but heroic experiments it's not as popular as it used to be. And in this study, what they have done is they recorded intracellularly from motor neurons in monkeys, in anesthetized monkeys. And this is so the motor neurons, this is the spinal cord, these are hind limb motor neurons. And they recorded intracellularly and stimulated over, they exposed the motor cortex, the area of the motor cortex, and they stimulate over the cortex and looked for sites with a monosynaptic excitation of the specific motor neurons. Okay, so this is really looking for cortical motor neuronal pathways. And in a way, I mean, this is the most direct way of understanding representation. So if kind of if in terms of when people think about maps, organized maps, you would assume that you'll have like a single patch that is connected to a single motor neurons, and this of course was not the case. And this is just the cortical area, so this is just looking at the cortical area that was exposed, and here this is the entire set of region where stimulation produced a clear monosynaptic response in motor neurons. And here what you see here is they recorded intracellularly from the deep peroneal muscle, motor neurons of the deep peroneal muscles, And they actually, here what they show is where is the cortical area where stimulation produces monosynaptic response. So these are strong monosynaptic response, and the blob around it is a little bit weaker monosynaptic response in different intensities of stimulation. So first of all, they found that it's roughly, it's a broad area that projects directly to a single motor neuron. But also, if you compare, this is in the continuous line, you see the input to these specific motor neurons, but if you compare it to areas that innervate the peroneus muscle, which is a synergist muscle, you can see, first of all, that peroneus has two patches of stimulation, and also there is a great overlap. But the peroneus is a synergist. But even if you look at antagonist muscles, like the flexor digitorum or the lucis longus or the tibialis, these two are antagonist muscles, still you can see that there is an overlap. So the same cortical site actually innervates monosynaptically different muscles that are not necessarily synergistic muscles. They can be also antagonist muscles. So that kind of makes it less likely that muscles are being controlled by specific sites in the motor cortex.
Can you explain antagonist muscles?
Sorry?
Can you explain the concept of antagonist muscles?
Okay, yeah. So like when I make this movement, I have the biceps that is like agonist for specific action, and the triceps is an antagonist. So they they have reciprocal relationship in terms of specific movement. Now, agonists and antagonists are usually kind of defined sort of a set of for the hind limb, it's very easy, because usually for the movement that we have for the leg, you have flexion, extension movements, and there is agonist and antagonist organization that is very precise. For the hand movement, it's less, it's the definition of agonist and antagonist is loose a little bit, because muscles that work as agonists in one set of movement can work as antagonists in other sets of movement. But in this case, this is the hind limb. These are kind of well-defined agonists. There is a synergist. Okay, synergist is usually the muscles that work together but not really work on the same joint. And antagonists, they work on the same joint but in often an anti-correlated manner.
Could it be that I'm just releasing the muscle and releasing the...
It's true. But when you're talking about cortical motor neuronal connection, it's only excitatory. Okay, so you're right. And actually, part of the experiment, they also recorded intracellularly from 1A inhibitory interneurons, which are the antagonists, sort of trying to see if this is really some sort of relationship. But at the level of the cortical, this experiment, they really looked for monosynaptic excitation. So there is no what you are suggesting. Okay, so, and that's for the hind limb, and later on people have done similar study at the forelimb, not as heroic in the sense, because the way they measured connectivity between cortical cells and muscles was not by recording intracellularly from the muscles, but averaging the EMG of the muscle over the spikes or over the stimulation from the cortex. Okay, so you stimulate in the... This is what we call spike stimulation averaging. This is a average EMG around activity of a single unit. Here, the unit is at time zero is the action potential of the specific unit, and you can see that in some muscles you have post-spike facilitation, and this post-spike facilitation is considered to be a reflection of a monosynaptic excitatory connection. And what they have shown is that in fact you can have a single site or single cell that is connected to multiple muscles, and that we know based on the work that I showed last time, the work of Shinoda, right, the tracing work, where he showed that a single axon from the corticospinal pathway can innervate multiple muscles, but also a single site can not only can affect different motor neurons, but remote sites can converge onto the same motor neuron. So it's a divergent convergent connectivity, and not necessarily continuous, which may suggest that this is sort of that muscles are not represented or well represented by some sort of a smooth, continuous cortical map. The other problems with the concept of map is that it has some, or we see what we actually, the results that we get are in part related to the method that we are using. And what do I mean by that? How do we measure cortical mass? We stimulate in the motor cortex. Now we stimulate the motor cortex or in the surface. We use a brief train of stimuli. We start to, you start with some sort of a level of 40 micro or 20 micrograms, and then you go lower until you reach threshold level, sort of that you see response, motor response only in 50% of the cases, something like this, right? I mean, so this is in a way you really look for just threshold or just supra-threshold response, or response at the level of the threshold for a very brief stimulation. And later on in 2007, Graziano actually used a much longer stimulation, supra-threshold stimulation. And the idea, that sort of the motivation for using a longer stimuli was the fact that in fact movement, the time scale of movement, if we're using for stimulation 50 microseconds, time scale of movement is hundreds of milliseconds, right? It's like 300, 500 milliseconds. So in a sense, there is no there is no correspondence between the stimulation study that we use for mapping and the properties of natural movement. So he actually used much longer train of stimuli, and what he found is that you don't see this discrete twitches of single joint as you see when you use a brief train of stimulation. Rather, what you see is a more natural type of movement. So the way he mapped is he found that along in the primary motor cortex there are sites that cause a movement of the hand to a specific subspace around the monkey, or manipulation at the central space, or chewing and licking, sort of movements that have what we think etiological meaning, right? So his idea was that in fact the representation of the motor cortex, or the movement representation of the motor cortex, is not of a single joint, rather of a type of movement or a goal of a movement, which is very different. Yes.
So can it be that cortical excitation or networks are if you give prolonged stimulation, then excitation spread out in the network and it tries to do something that it knows how to do. So
it's true. So we don't know when we're using a high-level prolonged stimulation. We don't really know what is the excitation. So this is the criticism against this type of work, because you don't really know. You probably excite large parts of the network in an artificial manner, but there was some. What you can say is that there was some organization of movement patterns. Okay, so it wasn't. First of all, it wasn't completely random, and there was some organization which may suggest that the peak of excitation is somewhere near the electrode, and it spreads out quite a lot, but you still get a meaningful type of response.
So in organization, you mean that when you feed the excitation in one area, you get this type of movement, and
yeah, in a sense, yes. So there were different types that possibly could span the repertoire of movements the monkey is normally producing. Okay? So this is again another problem. So if of the maps, right, of the concept of motor maps. You have to understand that the concept of motor maps is not that intuitive, because the motor cortex does not need to represent the environment, right? It doesn't need to represent the body. It needs to make movements. And the question is, and the underlying assumptions of a motor map indicate that we think that there is a someone that with like like a patch panel or a matrix that says, okay, we need to make this movement, will activate in organized manner. This is very difficult to think how a very well organized map will eventually generate a movement without just delegating the problems to another cortical area, right? But we know that the maps are not perfect, and also they are the outcome of the method of stimulation that we are using. The other kind of conceptual problems of the map is the fact that they are very, very plastic. So the motor cortical maps are extremely plastic in a way that makes it difficult to understand how the brain actually managed to use it in any meaningful manner. So this is the work of Ludo, that what he actually took a monkey and first mapped the motor cortex in a naive monkey that was not trained to do any specific task, and found these shoulder and elbow and finger representation. Then, after 12 days of training, okay, and the training was of a task that was involved digit movements, he saw that already after 12 days of training, there is expansion of the digit areas, okay? So, in red. So all these digit areas are suddenly larger. And you can see this very often. So you train a monkey to make a in a finger-related task, the digit area becomes huge on the expense of other areas. But if you now take the same monkey and train to do a shoulder-elbow task, all of a sudden the shoulder-elbow, at the same size that previously was a finger-related size, become shoulder or elbow-related size. Now this is kind of interesting from 2 points. First of all, what is the mechanism that allows such increased representation? And the other thing, I mean, this monkey can perform shoulder and elbow tasks with no problems. I mean, it's not that we see a deficit in his motor performances. However, the representation of shoulder and elbow is kind of smaller. So,
to what extent does the representation change with no explicit training? It's just by time?
By time, I mean, so the only way, I mean, normally, so most of these studies are done in like a trained monkey. So a monkey is already trained to some task, and then from day to day you stimulate it. You see that if you go back to the same site, I mean, oftentimes you get the same response. So a shoulder-related site throughout the course of weeks and months remains shoulder-related size. And if it shifts like to a little bit more distal or more proximal. So it can move one joint to either direction. So there is some noise in the map, but we don't know whether the noise is because there is changes in the same site, or because the electrode penetration, shifted a little bit left and right, and
So it's really obvious that the change here was mostly because of the training, and not.
And you can, and again, if you not train that monkey to a shoulder task, you'll see that these areas, the green area will already expand. It will expand on the expense of the red area. Okay, so yes, it is clear that it is task that is training related. So this is one type of plasticity. The other type of plasticity is an injury. So,
does he perform worse after the digit area? After, would it make sense for him to perform worse after learning to move the shoulders because it overlaps?
So I'm not familiar with this type of. So you're saying, okay, so we take a monkey, we train to finger task, then we train to a shoulder task, and now we go back to the finger task and see if the performances. So there are evidence that the extent of plasticity is related to the performance quality. Okay, so how well the monkey performs. I mean, if the monkey performs better, the expansion is larger. But obviously, I mean, it's not that the monkey has any other deficit. Okay, so it's not like that. But in the task, the performance of the task So there is something like tricky here, because the performance of the task has also something to do with the reward. So, do we really represent the act? I mean, it's kind of, what is really the representation tells us about? Tells about our motor ability or our expectation for reward. But this is kind of, I mean, it's not really well, these two components are not well accepted in these types of experiments, because reward is a major issue here. Okay, so the other type of plasticity that we see in the motor cortex is what is called injury-induced plasticity, and this is a work that was done in rats. And you can see that there is a map where you take a region in the primary, sort of the primary motor cortex of rats. I mean, in rats, the distinction between motor and sensory areas is not as well defined as in monkeys, but there is still a motor map. And you map it, and you see there is an area that's related to forelimb, to vibrissa, motor control of the vibrissa, which is very important for rats, and eyelids. Now you cut the nerve, the axons of the nerve that supplies the vibrissa muscles, right? So basically this is, you just cut the efferent muscle. And now you stimulate, and you see that the area that was previously vibrissa, okay, is now falling. So there is an expansion of other sites that are replacing the area that is lost, okay? So this is, and this takes few hours, okay? So after few hours of cutting the nerve, the entire map changes, although sensory input is the same, right? I mean, the sensory information, the afferent information has not changed, but the only thing you do, you cut the efferent, and the entire motor map shifts. And we think that this is due to that the okay. If you have a question, I mean, we have to answer. We think that the way we think about it is that there is a lateral inhibition. So the map, the motor map, is being shaped via lateral inhibition, intracortical lateral inhibition. So there is we think that neighboring area in the motor cortex are mutually inhibiting each other. So damage to the vibrician nerve reduce the strength of this inhibition, so that now stimulation in what was used to be a vibrissa area produces forelimb movement. So if this is the forelimb and this is the vibrissa, normally you have this. If you stimulate in the vibrissa, although there are also effectory connections, they are suppressed via this inhibitory connection. And as but as we cut the nerve, for some reason, this connection becomes weaker. Okay, this inhibitory lateral inhibition becomes weaker, and now we stimulate, and you see that you get you cannot get a vibrissa response because the nerve is cut, but the stimulation will activate forelimb area. And this was actually also confirmed, this hypothesis was confirmed using muscimol injections, and if we block this inhibition, you see that the map becomes blurred, areas become larger. So the cortical map in itself is not a persistent entity. It's not something that is hardwired in the system. It's not that when we stimulate, it's not that we only see the impact of the corticospinal pathways. There is a lot of intracortical circuitry that actually maintain these maps, but in response to injury, to training, you can see that these maps can kind of radically change, and the change is fairly fast. So maps are only useful to learn about the organization, but they may not be the way that the motor system actually controls movement. Now, in order to understand how the motor system controls movement, what we need to do is actually to study what are the motor-related activity of single cells in the motor cortex, and how they actually, what parameters of action, of movement are being directly controlled for by these motor cortical cells. Yes?
About the injuries,
Yes.
in the somatic nervous system, we see things like phantom pain.
Yeah, yeah.
So I was wondering if there's any equivalent phenomena in motor.
So I was thinking to add a slide. There are two interesting studies. One of them is studies of amputees, like people that the distal part of the hand was removed, and you can see that there is no phantom pain, but there is increase of representation of muscles above the area. And the other study that was also interesting is how people remapping of the motor cortex after implantation of implanting not artificial but a real hand. So now what they've done is they have someone that was the hand was cut in an injury after I think it was after a few years, maybe 4 years, but I'm not so sure about the time scale, but it was more than a year. He was implanted with a hand grafted from a person that had brain death. After brain death, I mean, they took the hand, not only the kidney, the liver, and that, but they could also take face or a hand, and they implanted the hand on this, and you could see the growth of presentation. So there is no equivalent of the phantom pain that we see, but there is a but it's not clear that there is a representation in the motor cortex of movement of the lost finger, so of the lost hand. Although recently, I think there is a recent paper in Crime Biology that tries to claim that, in fact, they were looking at amputees, people with fingers, and they did find representation of the lost fingers maintained in the motor cortex. So I have to be careful here. But in a sense, I mean, the kind of classical work suggests that other areas of the motor cortex take, the spared part of the arm takes over the lost part. But of course, I mean, it's difficult to say, you have to tell people, okay, try to imitate that you move, try to think that you move your lost arm. I mean, this is not a trivial task.
There's a mirror movement for phantom pain.
Yes. True, yes, that's true. I'm not from, I mean, I know there was a recent paper, I think even in the Alex they wrote about it. This is an ICMC student that is now in UCL did this work on amputees, but I'm not sure exactly, how, what are, I think there were still representation of fingers, but I don't know about like all arm, more distal part of it. So, I don't know if I answered or just confused you, but at least you can go and look at this. I can give you the reference of this paper. Okay, so now, I mean, we try to understand how movement is controlled by activity of single cells in the motor cortex. So in order to do that, and again, I mean, most studies are using non-human primates for this. I mean, and the reason is, there are two reasons for this. First, the motor system of primates is the most similar to the motor system of humans in terms of the control or the importance of the motor cortex in controlling movement. Motor cortex has a paramount impact on movement in animals located higher in the hierarchy. So if you want to understand that, if you want to understand what happens to humans in different states of disease or injury, we need to use animal models that is most similar. The other reason is that you can see, I mean, that you can train primates to perform well coordinated, precise, and accurate motor actions. You cannot train rats to do that. I mean, other than, of course, locomotion, but hand movements, voluntary movements of the hand in rats and monkeys are very, very different. So, I mean, it's like, if you want to understand the control of movement, you have to have the behavior that is appropriate for this stuff. And most of these studies were done in primates, and this is just to show you, I mean, this is the brain of a primate. Of course, in this case, this is just an example. They were recording from frontal areas of the primates, where motor areas is located, here, right? Just to hide them, but it's the central sulcus, this is the artery, the arm-related motor area is located somewhere here. And what you do is you kind of, this is the capsule of the cortex, and here, this is a recording. I mean, these pyramidal cells, you can actually, what we do is we use extracellular recording in most cases. Now you can do also intracellular recording or different types of imaging. But the most common work is recording extracellularly from activity of single cells, mostly pyramidal cells, just by numbers, right? I mean, because most of the cells of the cortex will be pyramidal cells. And you get activity, you get action potentials. Okay? I have to say that I think this is an example from spinal recording. Doesn't matter, it looks very similar. And what you often see is that within, I mean, when you record activity from a single electrode, you can actually identify the action potentials of multiple units. So we use the shape of the action. You've learned a little bit about spike sorting and so on and so forth. I mean, so you can actually identify activity of several units. And often in primates, you can use tens or hundreds of electrodes simultaneously and get activity of the entire area during movement. So in this case, doesn't matter. You can actually monitor the behavior, the motor behavior, and correlate between activity of cells and motor behavior. So the first experiments that were done in this type of work were already in the 70s. This is the work of Everts. And what Everts did, he trained a monkey to perform flexion and extension task, okay, flexion, extension task against, using a pulley and against a weight, a load. So, and the load could either resist or assist the movement. And he recorded activity of single pyramidal tract and non-pyramidal tract cells in the motor cortex, and he looked at the relationship between the position, which in fact is the force the monkey was performing, muscle activity, and single cell fire. So this is the movement of the monkey moved from extension to flexion, okay, against a load. You see that the flexor muscles are active, and the extensor actually become less active because this is sort of a reciprocal. You relax the extensor, you activate the flexors, and this is the activity of the single cell. So what is the first thing you see about the activity? Okay, this is action potential. Our assumption is that only the times of the action potential matters, right? I mean, because extracellular recording can only give us the timing, cannot give us anything about the shape or the synaptic inputs to this. So you don't really need to plot the entire trace, you just plot the times of the action potential. So what is the first thing that you see about the activity of the cell in relation to behavior? That's the cell. This is the behavior. Yeah. So it precedes the behavior. So there is some kind of predictive value of the activity to the behavior. There is also something about the fact that it fires first in a high rate and then goes to a little bit lower rate, but this is sort of probably related to the velocity. And but the activity is before, and this is now in relation to a flexion movement. Now we take the same we take the same paradigm, but now the monkey needs to make a flexion against a load. So he needs to make or exert higher level of muscle activity because he now has to kind of operate to a larger weight. So you see that the flexor muscles is really more active, and what happens to the activity of these cortical cells? It increases. So there is a relationship between the activity of the cell and the flexor and the activity of the flexor muscles. Now we had, instead of putting a flexor load that resists the movement, we are putting an extensor load that actually helps the movement. So now the monkey only, in order to move the hand, all it needs to do is to relax muscle activity altogether. And the weight via the pulley will just shift the arm passively. And you see that during this time, there is no muscle activity. I mean, the flexor muscles, there is a relaxation of the extensor muscles, and there is no activity of the cell. So this cell is in fact related. You can say that the activity of this cell is related to the force. And that was sort of the finding that in this paradigm of movement, one directional, flexion or extension, okay, so it's a one-dimensional task, flexion or extension, whatever found is that the activity of single cells in the motor cortex code for the force the monkey is performing in a single, or the joint force, but in a directional manner. So, flexion or extension, and so on and so forth.
Excuse me. Sorry, I'm a little bit lost. So, reflex and extension is controlled by two muscles?
Yes.
Two different muscles?
Yes. So, so it's like kind of, if you look at the flexor here, you have like maybe 6 or 7 flexor muscles,
right.
and you have like a little bit less extensor muscles, but there are several of these.
Okay.
But in general, they behave in a very correlated manner. So this is the flexor that makes this movement.
Okay.
Muscles can only contract. I mean, they cannot control movement to different directions. So the way you can only excite muscles, and then they can shorten, or you can relax this, but they cannot move to the other direction.
Okay.
So it's always this type of reciprocal organization.
So, and the CKN is the neuron.
The neuron, exactly, yes. Okay, so after the break, we'll talk about an alternative model for this that was suggested by Edwards.
If I give certain input, so like I give you becomes bigger.
כאילו, מה קורה? תשאל את דוד המנהל, ואז הוא עושה איזשהו חיבור. תראו, זה חוזר לאותם מקומות. אז הוא נוסע בבוקר מדוד המלך, אז הוא יסגר. ואז בלילה הוא חוזר לפנות את דוד המלך, אז הוא יסגר. זה בעיקר, זה לא שהוא יצא כמה פעמים.
You mean we could add a new fixed point? You mean add
אני גם, אבל כאילו אם את רוצה לצייר, כאילו בשביל לעשות, תמיד שאני מסתכלת, זה אני יכולה לעשות את הציורות שלי. טוב, יש להם פה כזה. זה נורא כאילו התגובה, הם עשו את הפיק, וזה סגובה, ועשו את באמת משהו
Yeah, they're like the models. It's more dynamic. And they're also models of forgetting memory.
זה עבר את הבדיקה של אלי. זה ממש של אלי, כן, כן, אני לא יודעת איך חשבתי על זה. כי דיברנו, זה בדיוק כזה, שהוא רצה היה במבה? כן, אבל לא היה, לא היה במבה.
כאילו, לא דיברתי אותו שעות, לא זה. אבל כאילו זה די לבד. ובסוף הדבר כאילו שחטאתי לדבק אצלנו. ובא לי, לא מתאים, שאתה יודע, וואו, אבל כאילו, כן, התרגיל הזה לא הסתדרתי איתה.
עוד פעם?
זה לא שאני לא הסתדרתי איתה, היא פשוט לא הסתדרה עם התרגיל.
בעייתי?
כן, אני לא יודע אם אני לא טוב בעבודה עם אנשים אחרים, או שאני לא טוב בלבחור את האנשים שאני עובד איתם, אבל אני מאחל לנו שיהיה לנו יותר קל. לא, אני מת מפחד. לא בגללך, בגלל האנגלית. אני צריך לדבר מה יש לי?
כמה אתה יודע לקרוא טוב?
כן, קראתי אתמול את המאמר על העכברים, לא עמדתי שזה, לא הצלחתי לפרק את כולו, אבל באיזשהו שלב קפצתי לריזולט, והריזולט שלו ממש מסתכלים טוב במקשר בין הספריאטים לכל.
כן? זה מה שחשוב, ההבנה
של... כן, איפה זה נכנס? אגב, הריזולט שלו לא כל כך מסביר למה זה קשור להתנהגות עם הריסטייטים. לא הצלחתי לעשות את הקישור הזה, אבל
איזה קישור?
אולי זה יתקדר.
קישור?
לריסטייטים.
שמה?
למה הפלסטיסיטי שם בסוף.
אז אני אסביר לך.
כאילו, אבל לא כרגע, אני חושב על זה אחרי, אני אקשר לי.
אין בעיה. לא.
אני גם...
כאילו, נדון על זה, אני חושב שאני מבין את זה מספיק.
אני אשמח שם את הדמות.
תקשיב, לא טוב. משהו. זה 5, זה 4, 5, 3, זה 2, איפה זה? איפה זה 2? מה?
שלום נורי, ועומרי מהשפק. היי, יש לך דקה? מעולה. עושים היום משלוח. אז עושים היום משלוח לירושלים. אז כמה בשבילך? וואו, סבבה. אז רשמתי לי. הוא צפוי להגיע היום בערב, ב-4 או 5 מברליסטן. זה בכיף יכול לחכות אצלי למחר. מחר בשעות הבוקר אני לא אוכל באוניברסיטה, פשוט תאמין לי, זה קצת של מחר. וואו, 30! איזה טירוף. איזה יופי, תודה לך. סבבה, איזה כיף. ביי ביי. וואו. ממש מקובל. צונח וחצי טוב.
אז היא לא הבינה, ממש אי אפשר לעשות דברים כאלה, זה בסוף. אז אנשים פוגעים, אז סימן שאלה של יום הולדת שמח, כל הזמן שזה הוא. אז הוא יאמר, גם אני, ואז הוא לא את. לא אני אסור.
אוקיי.
אני שמעתי מיד את ככה.
Everybody in their own.
הנה, 11 מגזים רוצים לעבור דרכי.
11?
שלא קצתי לעצבר לו?
תגיד,
אמרתי לך, לא. כן, ממש
לא, אנחנו ממש בסדר. אבל שאלו אותי אם אתה מדבר.
Okay. So the concept, the conclusion that was derived from these studies, set of studies, that activity of motor cortical cells control actually single muscles, or they code force level at not single muscles, but at a synergist probably level. So now, but this is sort of may also be related to the fact that the way the task was designed was a single joint task, and it's very difficult. There are too many parameters that are correlated. I mean, you cannot really distinguish between single joint to endpoint, to force and direction, and so on and so forth. So later on, about like 10 years later, a different paradigm was suggested by Georgopoulos. And what he did is he trained a monkey to perform a center-out task. Now, a center-out task is where actually the monkey is holding a manipulandum. Center-out. So the monkey actually needs to move the hand from a center position to one of 8 peripheral targets. And here, we don't really control for the single joint forces or torques that are generated. Usually there is not even a recording of muscle activity, but we monitor the endpoint position. And what he found is that in fact, and this is sort of just the traces the monkey generated, the monkey becomes very well in performing the task. And what he found is that the activity, if you record activity from single cortical cells, you get a picture that may be very different than what was suggested by
No, my computer
is dead. Okay. Well. No, you have such a tragic face. I don't know what to do. I mean, it's like I feel uncomfortable.
We just had a moment of silence.
Yeah. He needs a day of silence, I think. Okay, but I will continue anyway. So the activity of, if you record, so this is activity of a single cortical cell, recorded when your monkey performed movement to each of the 8 directions. And these are like 5 trials. It's 5 repetitions per direction. This is what we call raster plot. I'm sure you already heard about that. And time 0 is movement onset. Now, you can see, first of all, you can see that the cell changes its rate as a function of direction, right? There are sort of directions that it prefers. This target number 5, target 4, target 6. And there are directions that are non-preferred. Yes?
Those are single cells that are...
No, it's a one cell,
Oh, wow.
and repetitions, 5 repetitions per target. Okay? Because you want to show that you have like a sort of a stationary, repeatable, reproducible result. This is sort of just so we often make several repetitions per condition. And again, in the preferred target, in the preferred directions, you can see that the activity starts before the actual movement. So again, there is sort of a causal relationship between activity in the motor cortex and the movement, okay? It's not only feedback, because if activity only, like if you record from sensory cortex, most of the cells, the activity will lag movement because they are being driven by the proprioceptive feedback. But here, even before feedback starts, you already see activation of the cell. And what he defined is a preferred direction, because you can compute the activity of the cells around movement, and you can identify what is the, by vector summation, what is the preferred direction of the cell. Now, interestingly, not only did the cell increase its rate to one direction, it decreases its rate from baseline level in the direction located in the opposite direction. I mean, the opposite target or the opposite direction. Okay, so and if you look at if you plot the activity of the cell as a function of direction, okay, what you get is a tuning curve, basically, right? I mean, so this is the activity of the cell, activity as a function of direction, and you can see that this is the preferred direction, and you can fit fairly well the tuning curve of motor cortical cells with a cosine function. So there is not a lot of changes in the width of the tuning. The tuning is relatively broad. It's not a single target. It's a broad tuning curve with some sort of a preferred direction. And the tuning appeared to be, or the preferred directions were uniformly distributed in space. Okay? So there was a single, all directions were evenly represented by the activity of motor cortical cells. Yes?
I'm not sure how how you know that what's coded here is direction, because probably it has a connection to the way the muscle moves and...
That's true. I mean, but that's sort of but in a way, what was striking, I think, that in terms of joints, torques, these movements are very complicated in a way, because some of them have more shoulder movement, some of them have more elbow movement, their interactions. It's a very complicated task in terms of in the joint space. Surprisingly, the activity of the cells was very simple, right? I mean, it appeared to be not well, or not related. The simplicity was sort of at odds with the complexity of the motor task. So, but you're right, and I'll show you now a set of experiments that were really trying to dissect these muscles and the direction, and all the parameters that are here are just a kind of lumped together. Yes?
Is the angle measured relative to the body frame, to the visual input, to what?
To sort of it's basically the angle is to the starting position.
Yeah, but let's say it's like the head of the monkey was like tilted to...
Yeah, or like if you look at the space, a different starting position, for example. Like if you start here, I mean, instead of tilting the head of the monkey is difficult in experiments because, it's kind of, usually the head is fixed. So, but so all these experiments were made, and you can see that there is a modulation of rate as a function of the space. So, for example, the center position has some, or the initial position has some impact on the rate level, but the properties are not strongly affected by this manipulation. So, sort of, in a way, the view of Physiology was that the motor command is rather abstract. It is moving there, independent of the details of the muscle properties or the joint angles or the specific space relationships. Okay? His idea was that the fact that the motor cortical cells code direction of action in rather abstract manner. And in a way, it kind of started to... So, what he suggested is that basically the important component of motor cortical activity is the population vector. So each cell has a preferred direction, right? And you can actually compute a population vector by sort of a vector summation across all cells. Okay, so of course, I mean, he didn't have all cells. I mean, he didn't even sample the cells simultaneously. So every day he record like few cells, usually at sequence, and he then assumed that there is no interaction, the correlations are not important here, and he computed the population vector as a function of time. And the population vector is in fact some weighting, some weight value that was computed, and the preferred direction of the neurons. So, and the weight is basically the rate, at the average rate at the epoch of the cell I at epoch I, minus the baseline fire rate. So, what you see is that basically the population vector will be, you basically multiply the preferred direction of the cell with some weight value, and the weight is basically the instantaneous rate of the cell relative to baseline level. So if the cell increases a lot, the rate, if the movement is at the preferred direction of the cell, the firing of that cell will be very high relative to baseline, and it will contribute a lot. It will push the system very strongly to that direction. But if the cell is, if the preferred direction of the cell is at 90 degrees to the movement, okay, you're moving here, but the preferred direction of the cell is that, the firing rate of the cell will be small, and its contribution will be relatively small. And this is just an example of how you compute a population vector when at movement to different directions, right? So each of these lines is the contribution of a single cell. Each of the black line is a contribution of the single cell, so you see to different directions, and you don't see how come you don't see lines pointing to this direction?
The weight is 0.
It's not 0, but it is minus. It's negative. So basically, it points to that direction because it's a negative. Okay, but in any way, you can see that because directions are uniformly distributed, you have even numbers of lines pointing to directions off above the preferred direction, the movement direction, or below the movement direction, and these all cancel out in a way, and only the vector summation, the summation of these vectors will generate a population vector that points to the actual movement of the monkey. Okay, so these population vector, the idea is the population vector instantaneously track the movement of the monkey, and I think I have an example here. So what you see here, the monkey was actually required to follow a cursor that was in a spiral in space, and you see the blue lines are the contribution of single cells, and there is a yellow is the, okay, so I can't remember if yellow is the actual movement and white is the population vector, or the other way around, but it doesn't matter. You'll see in a second that the population vector very nicely follows the movement of the monkey was to the cursor movement. So even again, independent of what exactly the activity of single cells in motor cortex is coding for, computing the population vector will generate a very good prediction of the actual movement. Okay? So, but now, I mean, we need some more information. I mean, also, the Georgopoulos and his colleagues did several additional studies to actually confirm this hypothesis, or their hypothesis. And here what they did is they introduced a delay period. So the monkey got a cue that told him, okay, you're going to move to this direction. But he had to wait for a variable delay period until a go signal actually arrived. So during this time, there is no movement, but the information is already there. Okay? So at the delay period, the monkey is not making movement, There is no feedback, there is no muscle activity, but he knows what type of movement he will have to do. And we know that this type of delay actually, this prior information shortens reaction time. So the monkey is actually using, or people too, we use this information to pre-plan the movement. And what he showed is that if you compute the population vector, you can record activity of motor cortical cells at that time, and you see that the activity of cells is already tuned during the delay period activity. And the population vector points to the future direction of action. Now, the interesting part is that, in a way, the tuning, or you compute the preferred direction of cells based on the movement-related activity. But you see that, in fact, the tuning of the cells at this time can be very different. Still, the population vector is very robust and will actually show this activity, the future movement already during the delay period, before movement started. A little bit more interesting experiment that he did and was the mental rotation task. And what he did is he trained a monkey to do two types of movement. So this is related to your question. So the first one is the monkey got a cue and he had to move to where the cue came from. Okay? And this is what's called the direct movement. There was a direct, the movement was to the target that was cued. In another set of trials, the monkey had to do some rotation. The movement had to be in 90 degrees to the cue. So if the cue was here, the movement had to be 90 degrees to the movement. And what he found is that in the direct trials, and again you have a delay period, in the direct trials, population vector actually soon after the stimulus occurred, the population vector points to the direction of movement. But this is not only direction of movement, this is also the direction of the cue, right? These two parameters, the cue and the movement, are aligned. However, when there was a separation, angular separation between the cue and the movement, the population vector started by pointing to the cue, and then during the trial, population vectors rotated and pointed to the movement.
You see it in the movement, so it goes like...
No, because there is no movement at this time. It's during the delay period. So it's a mental rotation. That's why this is sort of, that's how they call this properties. There was a mental rotation that actually corresponded to this shift between the cue and the movement the monkey had to do in order to properly execute the task. Okay? And you can see it here. This is the population direction. Okay? And you see that in the direct trials, already soon after cue onset, the population direction is already pointing to the direction of movement, which is also the direction of cue. But in the rotation trials, you can see that the movement, that the population vector first points to the movement and then shifts in 90 degrees to the action. Okay? So his idea, is that the population of cells in the motor cortex actually are responsible for this transformation from visual information to motor command. And this is the evidence that this really took place. So the problem is, in a way we have like these two different models of motor cortical activity. The one model of ever, say cortical activity codes for activity of single muscles, or force, or codes for the muscle force, right? This is sort of the activity that we showed first. In this, in the job, and this is kind of nice because it says that there is the motor command already specify action in muscle-based coordination. However, the model suggested by Discontinuities talks about motor command as being more abstract, being direction, and there is, but this really leaves the problem of where this translation from this abstract representation of movement direction is into muscle command takes place, right? I mean, at the end, the muscle needs to get some sort of input that will tell it, look, this is the movement that we need to do. So, thinking about abstract and the idea of Discontinuities suggesting that the basically motor command is defined, motor cortical command is defined in external coordinate frame, leaves us with the problem of where does it actually translate it into muscle-based coordinate frame. So, and what Discontinuities suggested is that in fact, and this is using a different set of experiments, we have downstream sets of motor primitives, and these motor primitives are able to receive motor command, abstract motor command, and translate it into specific type of movement. And what do I mean by this? So there was a study basically in the frog, right, of Beatty and colleagues that suggested that what they did is they stimulate in the spinal cord, at different sites in the spinal cord, and while the frog, the leg was sort of anchored at different location in the space. So you move the leg of the frog, you just pin it to different sites in the field, and they measure the torque the leg was generating, the forces the leg was generating in response to this intraspinal stimulation. And what they found is that different stimulation sites produce. So this is different. Okay, so these are different. A, B, C, D are different stimulation sites. And here, this is the field, the force field that was generated by stimulating in a single site. And here, the leg of the frog was positioned here, or here, or here, or here, right? Okay, along the space. And you can see that no matter where the leg was positioned, stimulation actually generated a converging force field, right? All sort of the force field was trying to move the leg to a specific location here, right? This is a converging force field. And in a different site, there was a different convergent point, and so on and so forth. And they found, first, there are few stereotypical fields that were generated by intraspinal stimulation. All the fields were converging into point within the field. It wasn't just like trying to shift the leg to some outside of the field. I mean, these were converging fields.
How did you define the field?
So a field. So if you look at this is the frog, and this is the leg of the frog. Okay. So now, this is a headless frog, right? I mean, they cut the connection above the tectum, so it's only spinal circuitry that operates. Now you pin the leg of the frog here, you stimulate in the spinal cord in this point, and you see the force going here. Now you pin the leg of the frog physically, right? The same frog, but now you pin it here, and you see a force field pointing here. And that's how you map the field, okay? And you see the arrows here all point to specific converging point within the field, okay? And they found that there were not a lot of, there were few stereotypical fields, okay? So A, B, and C, and D, this was sort of the types of fields that were obtained. That was one thing. But what was more interesting, if you stimulate at two different points, the field that you get is a linear summation of the two singular fields, okay? So you get this field here, and when you stimulate at point C, and when you stimulate at point D, you get this field. Now you stimulate simultaneously at point C and D, and what you get is a linear summation of these 2 points. So it's a large set of experiments which I won't really go, but they suggested that in the spinal cord there are few motor primitives that superpositioning these primitives can actually span the entire spectrum of movements the frog was generating. Now, it's a bit of a leap, right, going from this frog to the primate, but still, you can think that the motor in the, you can think that there is in the spinal cord, we have a kind of a primitive, motor primitive, sort of a building block for action. So, in a way, all you do is you have to know the motor cortex, all it needs is to send the right signal to these synergies, and each synergy is controlling a set of muscle. And so this is one synergy, and this is activation of 5 different muscles. This is pattern of activation of 5 different muscles, and this is a different synergy that activates differently the same muscle. And all you send is a activation coefficient function for this synergy and that synergy, and you get a complicated movement. Is this point clear? You look a little bit shocked, and I don't know if this is sort of my fault or the tragic event of the of earlier.
The activation coefficient?
So activation coefficient is just activation as a function of time that you send to this muscle synergy. It could be a population vector, or like any type of activity that is not directly related to the activation of single muscles. So if upstream cortical command will only know the synergies that are available and what are it could learn by experience what are the activation coefficients that are required to be sent downstream in order to get a complicated action. So there is some sort of intermediate step of translating a simple, relatively simple command into very complicated patterns of muscle activation. So the motor cortex doesn't really need to know anything about, the complexity of the different muscles, the interactions between different joints, and so on and so forth. There is an intermediate layer that translates a relatively abstract command. And without us knowing what are the synergies, we will not be able to decipher the command in terms of a low-level properties. Okay, if you ask questions, it seems like there are questions. There is a hidden layer of uncertainty here that I'm not reaching somehow. Yes?
So I'm not sure what is seen in the motor cortex.
In the motor cortex, we see this sort of an activation signal. And the spinal cord, these activation signals are correlated. So what you see here, let's assume we have only 5 muscles. So one synergy activates, this is the pattern of muscle activation that it has. The other synergy has a different pattern. Now you can think of there are multiple synergies, but not the number of muscles is very, very large, right? So the question is whether motor cortical command specify each single muscle activation, and we think this is not reasonable because there are just too many muscles, and we see that the organization, the map of the motor cortex is not at a single muscle level. So there is some sort of a layer between motor cortex and single muscle, and one option is that these synergies, they could also be like cortical synergies, but the idea of George is that these are sort of subcortical synergies that they are defined. Each synergy, there is no plasticity within a synergy, but what the motor cortex needs to learn is who are the available synergies and what coefficient needs to be sent downstream. Yes?
Do this hidden layer, most of the API, is it built in, or what guides the learning of this?
Okay, so in a sense, it could be, the idea is that these are built in, sort of, it's like, I let you play with Lego. I give you, these are the blocks, okay? You cannot cut a block, I mean, you could basically, but it's not recommended. This is not part of the game. You get the building blocks. These are hardwired via, the reflex pathways. So reflex pathways are sort of hardwired, you know, but the learning of these, how to play with this and what you can do with this is a learning thing. This is the corticospinal pathways, you know, it can learn. There is some learning process or of activating these synergies, and there could also be some learning process in the motor cortex that is continuous throughout life. You know, the corticospinal connectivity sort of takes place in a critical period, but then you can also keep on learning by changing these activation coefficients by learning later on learning process. Okay, but the building blocks are sort of hardwired. Ideally. Yes.
I have a question about the monkey experiment.
Yes.
If you see the activation of the motor cortex even before there is movement,
yes.
So there needs to be a gating mechanism.
Okay, that's a huge question. It's not a. Okay, so this is a major problem, right? I mean, the motor cortex is very active already before, and what is the gating mechanism? Now, it depends whom you ask. So some people, like me, will say, yes, there is a spinal gating mechanism via premotor reticulospinal pathways that we said before that it can have an inhibitory impact. So part of the preparatory activity that is mostly seen in premotor cortex, I didn't talk about that, but in premotor cortex, most of the activity is preparatory. And this preparation is translated into gating mechanism at the spinal level. More recently, there is another concept that talks about that in the motor cortex, activation of populations in the motor cortex can be either in a potent space that will produce movement, or can be in an impotent space, null space. A space, so you can look at the activity of cells, and in the subspace of this subspace of the activation is null, that will not produce muscle activity. And because you can think of the activity in the motor cortex as a multi-dimensional. Okay, it's a huge dimensional space, right? All cells, each cell actually is a one dimension, so the activity is a large, very high dimensional space. And part of this space generates movement, and activity in the other part of the space will not generate a movement. Just because of its connectivity pattern, it will cancel out and so on and so forth.
What will be the logic of the body to make such a null space?
The null space, in a way, it can let you plan things or do a lot of computations in the motor cortex without risking in generating it into a movement.
Like a draft.
Yes. Yes. So all the planning takes place in this draft or the null space. But of course the question is how do you shift from the null to the potent space? And also it gives you a description but not a mechanism, you know. But you can learn this, right? I mean, you can learn what is the null space, what is the potent space, and you can shift, you know. It's a very elegant way to think about activity in the motor cortex, because this problem that you are saying, this is a major problem, right? I mean, for example, if I play you, the monkey is performing a task, there is activity in the motor cortex. Now the monkey, we just stop the task. The hand is locked. The monkey is not doing anything. The motor cortex is as active as during movement. And in fact, for 40% of the cells in the motor cortex, the active is more so, more than in. Now, the problem is that we find it difficult to identify the cells. So, if most of the cells that are more active during spontaneous activity are inhibitory cells, then you can say, no, this is a gate mechanism. If this is not the case, if you have the same, the increase in activity both for excitatory and inhibitory cells, then you can think about null space. Okay, but this was a long answer to. Okay, any more questions? So this interface, this intermediate layer, could actually translate between the motor cortex, the command, an abstract command, and low-level muscle representation. I mean, is this point clear? Okay. So there are other problems with this, the idea of Georgopoulos. For example, how can a high-level cortical command adjust motor behavior based on the ongoing context or the ever-changing world? So, for example, if we are, we are facing environmental forces or any other type of interactions with environment that can change with time, the high-level cortical command that Georgopoulos said has basically no access to this information, because it is very abstract and it's not clear how these ongoing changes in the environment will affect the command. And we know the command can change, but it's not clear how these abstract commands interact with the environment. And the other, even more problematic issue, I mean, there is also the issue of kind of that in fact the same type of results that we see can be an outcome. The same type of activity can be outcome of a very different coding mechanism. But one of the major problems is the fact that the underlying assumption of Georgopoulos is that the preferred direction of cell is a stationary property. This is a non-changing property of the cell. Because if the cell keeps changing its preferred direction, how can you compute anything? I mean, if you don't know, you cannot rely on the preferred direction of the cell. And we know that cells can change their preferred direction as a function of many different, of context of task, of posture. So this is the work of Scott and Kalaska that actually trained the monkey to perform movement, the same type of movement, center-out movement, but a different hand posture. So one of them is like the monkey was holding like this, the manipulandum, and in another posture the monkey was, there was an abduction, shoulder abduction, and they found that the preferred direction of single cell can drastically change between the natural position and the abducted position. And this is just activity of several cells during the reaction time, and this is the population vector, and this is during reaction and movement time, and this is the entire task period. And the same cells, now if the monkey is in an abducted position, has a very different preferred direction, and also the population vector based on these cells changes as well. So there is a problem of how the activity of single cells is not, the preferred direction is not a constant properties of cells. Nevertheless, if you take enough cells, if you elect a large fraction of the cells, you can still compute, the population vector is robust. So even though activity of single cells can change in terms of the preferred direction, the population vector will still point to the direction of movement, because apparently there is still the variability is random, so it cancels out in a way. So the preferred direction slips in a random manner, but still enough cells have a persistent preferred direction that the population vector will still point to the actual position. And this concept of population vector, that pointing to the movement of action or the desired movement of action, has been recently used a lot in brain-machine interface. So we can actually train a monkey to make movement and control a cursor, but then when the monkey stops, we can train the monkey to control the cursor just by thinking about movement without actually performing the movement. And the way so what we do is we take the activity of the cells, we record the activity of motor cortical cells after we define their preferred direction, and we use this preferred direction in the population vector in order to control a cursor, and the monkey can learn how to control a cursor by mental processes alone. So population vector is a robust property, even though single cell properties can be quite noisy. Yes?
Isn't the changes in, like, can't it also say that these cells compute things that, like Nova said, regarding the motor unit, because it's the same movement?
Exactly. Okay, so this is exactly a point that was suggested, and so in the remaining minutes that I have, I will show you an experiment that directly tried to answer this and how we actually translate or how coordinate transformation takes place in the motor cortex. So in all these experiments, you know, the movement of the monkey was sort of always in the same, or there was no like a continuous exploration of what is the relation between the direction of movement and the activity of the underlying muscle activity. So this is a work that Peter Strick started in 1999, and what he did is he trained a monkey to perform center-out tasks, okay, using the wrist only. So there was no, it makes it easy because the wrist is a sort of quite symmetric type of joint. You know, you can it's a single joint, so it simplifies in terms of the computation in the motor cortex, but it can move to all these, generate torques to all different directions, or can make movement. And the monkey was trained to perform the same task of center out to one of 8 directions, but a different hand posture: pronation, mid position, or supination. And you can train a monkey. I mean, it's not easy. In the first paper, they only had one monkey. I mean, usually, this is unique. But they said that it took them 8 years to train the monkey. I mean, which is kind of actually, I was there in one of these recordings. This is not a monkey. This is I don't know, King Kong. I mean, this is this giant monkey that everybody's afraid of, and he needs to have the technician sitting next to him because otherwise he gets really nervous. I mean, it's really funny. It was very funny type of experiment. But it took them a very long time to train the monkey because the supination is not easy. Okay, and so you can see that the monkey, the visual space was constant, right? So upper target or lower target, these were the same, but the muscle pattern that you need to generate in order to reach these different muscles can dramatically change, right? So let's look at pronation versus supination. So in pronation, in order to get to the upper target, what you need is what type of muscles you need to activate? Extensor. Okay, you generate extension. So these are extensor muscles. Now, to get to the same target, but during supination, with the posterior supination, what you need to do is you need to generate flexion movement, right? Yeah. So this is a flexion. Okay, these are all the flexors. Pronation and supination. This is here. This shows in the figure. This is pronation, and this is supination. I don't know why is it called like that, but that's kind of pronation and supination. This is kind of anatomical terminology. So, but now what we can do something very simple, right? We can measure the tuning curves of cells in a pronation and in supination trials. Let's forget about the mid position because it only complicates things. But what can we, if cells in the motor cortex only code direction, like abstract the direction of target in space, how much the preferred direction will shift from this to this? If it's only abstract representation. Sorry? It shouldn't. There should be a zero shift in preferred direction between pronation and supination because the target, the space didn't change. If motor cortical cells dictates or code movement in joint space. What should be the shift? How many degrees do we shift from pronation to supination? 180. Now, what if the coding is of muscles? What would be the change in the... If motor cortical cells code muscle activity, how much they should shift from pronation to supination? Okay, so this is difficult because it's not clear. So what you can measure it, right? You measure the preferred direction of muscles, relevant muscles, during pronation time. Then you measure the preferred direction of muscles during supination trials, and you can measure the shift of you can measure the shift in preferred direction of muscles. Okay, so and that's what they did. They measure this is the shift in preferred direction of muscles, of forearm muscles, and you see it's about 70 degrees. So now, when we measure the cells, we can use the shift in preferred direction to understand the coordinate frame, right? If cells will have 0 degree of shift, then it means that they code information in an extrinsic coordinate frame. If they had 180, they code in the joint coordinate space, and if they have 70, they code in muscle base. Now, what they found is cells in the motor cortex have bimodal distribution. There is a subgroup of cells with near 0. It's not really 0, it's like 30 degrees shift in preferred direction. And there is another group of cells, or there are at least, it's not necessarily an independent group, it's not necessarily an isolated group, but there is a large number, or relatively large number of cells that have their shift in PD is like muscles. So you can say that in the motor cortex, there is a representation of space and muscle, and the coordinate frame, the translation from space to muscle, takes place here at the level of already within the motor cortex. Now, we actually repeated this task, but by recording in cortical cells and spinal cells simultaneously. Now, what would you expect to find the PD shift at spinal neurons, at the level of the spinal cells? Like muscles, exactly. It should be like the muscles, because if the translation takes place in the motor cortex, spinal cells should already be at the muscle coordinate frame. But more importantly, you expect that the coordinate frame of cortical cells that are connected to spinal neurons to be only for muscle-based cortical cells, right? Because what you have is the concept they had was that you have, it will take me 2 minutes just to finish this point. So you have in the motor cortex, you have space, and muscles, and the translation is like this. In the spinal cord, you expect to have only muscles. So you expect that these will be the output cells, right? But what we found is that what you see here, this is the delta PD as a function of time, from cue onset to movement onset, of cortical cells in red and of spinal cells in blue. And you can see that just before movement, on average, motor cortex is, before movement, is still in somewhere between external to internal coordinate frame. The average shifting degrees of cortical cells is about 30 before movement. So it's not external and it's not internal. But at that time, spinal cord is already at muscle-based coordinate frame. So the idea that we had is coordinate frame is not a static properties of motor cortical neurons. From cue onset till movement, it continuously it's not only that there is a mental rotation, there is an entire shift of coordinate frame. Because at movement onset, the dominant information is visual information. It's a space information, where the target is. And motor cortex codes this information. And as movement starts and motor plan is emerging, coordinate frame slowly shifts towards external. But before movement starts, while motor cortex is somewhere in between, spinal cord is already at internal coordinate frame. So that cortical, the idea that we have is that in fact you have most of the motor cortex is external, and there is a connection both of external and internal, and the corticospinal termination pattern in itself actually contributes to this, to finalize this translation from external to internal coordinate frame. So it's not that everything is completed in the motor cortex and the motor cortex sends out a final muscle-based command. The corticospinal interaction in themselves contributes to the finalizing this translation of external space to internal representation. But the important part for me is the fact that the representation of space is dynamic. Coordinate frame is not a fixed entity of an area, of the motor cortex. The motor cortex speaks at different coordinate frames depending on the time. Okay, so we're going to meet this Thursday. There's going to be only one. I will first start by. There will be one presentation. I will start. The first hour will be devoted to finalizing, because I cannot let you go without hearing a little bit about the premotor cortex, which is kind of really interesting part of the brain, and then Mo and Tal, right? They will describe the mirror system in the premotor cortex. So, I'll see you Thursday.